Hello friends, in today's lecture we shall be talking about the digital logic families, the most important concept in digital electronics. In fact, digital integrated circuits are produced using several different circuit configurations and production technologies. Each such approach is called a specific logic family. The key ingredient within any integrated logic device, be it a logic gate, a multiplexer or a microprocessor, is the transistor. The kind of transistors used within the integrated circuit to a large extent specify the type of logic family. The two most popular transistors used in ICs are bipolar and MOSFET transistors. In general, ICs made from MOSFET transistors use less space due to their simpler construction, have very high noise immunity and consume less power than equivalent bipolar transistor ICs. However, the high input impedance and input capacitance of the MOSFET transistors result in longer time constants for transistor switching speeds when compared with bipolar gates and therefore typically result in a slower device. But over the years of development, the performance gap between these two technologies has narrowed considerably. Types of logic families. The entire range of digital ICs is fabricated using either bipolar devices or MOS devices or a combination of the two. Different logic families falling in the first category are called bipolar families, and these include diode logic, resistor transistor logic, diode transistor logic, transistor transistor logic, emitter coupled logic, also known as current mode logic, and integrated injection logic. The logic families that use MOS devices as their basis are known as MOS families, and the prominent members belonging to this category are the PMOS family using P channel MOSFETs, the NMOS family using N channel MOSFETs, and the CMOS family using both N and P channel devices. The BIMOS logic family uses both bipolar and MOS devices. Of all the logic families listed, the first three, that is diode logic, resistor transistor logic and diode transistor logic, are of historical importance only. Diode logic used diodes and resistors and in fact was never implemented in integrated circuits. The RTL family used resistors and bipolar transistors, while the DTL family used resistors, diodes and bipolar transistors. Both RTL and DTL suffered from large propagation delay owing to the need for the transistor base charge to leak out if the transistor were to switch from conducting to non-conducting state. TTL and CMOS devices are grouped into functional categories that get placed into either 7400 series or the 4000 CMOS series. Now, another series you will run into is the 5400 series. This series is essentially equivalent to the 7400 series with same pinouts, same basic logic function, but it is more expansive chip because it is designed for military applications that require increased supply voltage tolerances and temperature tolerances. For example, a 7400 IC typically has a supply voltage range from 4.75 to 5.25 volt with a temperature range from 0 to 70 degree centigrade, while a 5400 IC typically will have a voltage range between 4.5 and 5.5 volt and a temperature range from minus 55 to 125 degree centigrade. Figure here shows the simplified schematics of a 2-input AND gate using diode logic, a 2-input NOR gate using RTL, and a 2-input NAND gate using DTL. The DL, RTL and DTL families, however, were rendered obsolete very shortly after their introduction in the early 1960s, owing to their arrival on the scene of transistor logic. Logic families that are still in widespread use include TTL, CMOS, ECL, NMOS and BiCMOS. The PMOS and I2L logic families, which were mainly intended for use in custom large scale integration circuit devices, have also been rendered more or less obsolete, with the NMOS logic family replacing them for LSI and VLSI applications. TTL family of ICs. The original TTL series, referred to as the standard TTL series, was developed early in the 1960s. This series is still in use, even though its overall performance is inferior to the newer line of TTL devices such as the 74LS, 74ALS and 74F. The TTL family has a number of subfamilies including standard TTL, low power TTL, high power TTL, Schottky TTL. The ICs belonging to the TTL family are designated as 74 or 54, 74L or 54L for low power TTL, 74H or 54H for high power TTL, 74LS or 54LS for low power Schottky TTL, 74S or 54S for Schottky TTL, 74ALS or 54ALS for advanced low power Schottky TTL, 74AS or 54AS for advanced Schottky TTL and 74F or 54F for fast TTL. A 2, 3 or 4 digit numerical code tells the logic function performed by the IC. It may be mentioned that 74 series devices and 54 series devices are identical except for their operational temperature range. The internal circuitry of a standard TTL 7400 NAND gate along with a description of how it works will be provided in next lectures. CMOS family of ICs. While the TTL series was going through its various transformations, the CMOS series entered the picture. The original CMOS 4000 series or the improved 4000B series was developed to offer lower power consumption than the TTL series of devices, a feature made possible by the high input impedance characteristics of its MOSFET transistors. The popular CMOS subfamilies include the 4000A, 4000B, 4000UB, 54/74C, 54/74HC, 54/74HCT, 54/74AC and 54/74ACT families. The 4000A CMOS family has been replaced by its high voltage versions in the 4000B and 4000UB CMOS families, with the former having buffered and the latter having unbuffered outputs. 54/74C, 54/74HC, 54/74HCT, 54/74AC and 54/74ACT are CMOS logic families with pin compatible 5474 TTL series logic functions. The 4000B series, though more energy efficient than the TTL series, were significantly slower and more susceptible to damage due to electrostatic discharge. Characteristic parameters of logic families. Here we will briefly describe the parameters used to characterize different logic families. Some of these characteristic parameters, as we will see in the discussion to follow, are also used to compare different logic families. High level input current. This is the current flowing into or out of an input when a high level input voltage equal to the minimum high level output voltage specified for the family is applied. In the case of bipolar logic families such as TTL, the circuit design is such that the current flows into the input pin and is therefore specified as positive. In the case of CMOS logic families, it could be either positive or negative, and only an absolute value is specified in this case. Low level input current. The low level input current is the maximum current flowing into or out of the input of a logic function when the voltage applied at the input equals the maximum low level output voltage specified for the family. In the case of bipolar logic families such as TTL, the circuit design is such that the current flows out of the input pin and is therefore specified as negative. In the case of CMOS logic families, it could be either positive or negative. In this case, only an absolute value is specified. High level output current. This is the maximum current flowing out of an output when the input conditions are such that the output is in the logic high state. It is normally shown as negative number. It tells about the current sourcing capability of the output. The magnitude of high level output current determines the number of inputs the logic function can derive when its output is in the logic high state. Low level output current. This is the maximum current flowing into the output pin of a logic function when the input conditions are such that the output is in the logic low state. It tells about the current sinking capability of the output. The magnitude of low level output current determines the number of inputs the logic function can drive when its output is in the logic low state. High level input voltage. This is the minimum voltage level that needs to be applied at the input to be recognized as a legal high level for the specified family. For the standard TTL family, a 2 volt input voltage is a legal high logic state. Low level input voltage. This is the maximum voltage level applied at the input that is recognized as the legal low level for the specified family. For the standard TTL family, an input voltage of 0.8 volts is a legal low logic state. High level output voltage. This is the minimum voltage on the output pin of a logic function when the input conditions establish logic high at the output for the specified family. In the case of the standard TTL family of devices, the high level output voltage can be as low as 2.4 volt and still be treated as a legal high logic state. It may be mentioned here that for a given logic family, the VOH specification is always greater than the VIH specification to ensure output to input compatibility when the output of one device feeds the input of another. Low level output voltage. This is the maximum voltage on the output pin of a logic function when the input conditions establish logic low at the output for the specified family. In the case of the standard TTL family of devices, the low level output voltage can be as high as 0.4 volt and still be treated as a legal low logic state. It may be mentioned here that for a logic family, the VOL specification is always smaller than the VIL specification to ensure output to input compatibility when the output of one device feeds the input of another. Propagation delay. The propagation delay is the time delay between the occurrence of change in the logical level at the input and before it is reflected at the output. It is the time delay between the specified voltage points on the input and output waveforms. Propagation delays are separately defined for low to high and high to low transitions at the output. In addition, we also define enable and disable time delays that occur during transition between the high impedance state and defined logic low or high states. TPLH is the time delay between specified voltage points on the input and output waveforms with the output changing from low to high. TPHL is the time delay between specified voltage points on the input and output waveforms with the output changing from high to low. Fan out. The fan out is the number of inputs of a logic function that can be driven from a single output without causing any false output. It is the characteristic of the logic family to which the device belongs. It can be computed from IOH divided by IIH in the logic high state and from IOL divided by IIL in the logic low state. If in a certain case the two values IOH by IIH and IOL by IIL are different, the fan out is taken as the smaller of the two. This description of the fan out is true for bipolar logic families like TTL and ECL. When determining the fan out of CMOS logic devices, we should also take into consideration how much input load capacitance can be driven from the output without exceeding the acceptable value of propagation delay. Maximum clock frequency. This is the maximum frequency at which the clock input of a flip-flop can be driven through its required sequence while maintaining stable transitions of logic level at the output in accordance with the input conditions and the product specifications. It is also referred to as the maximum toggle rate for a flip-flop or counter device. Power dissipation. The power dissipation parameter for a logic family is specified in terms of power consumption per gate and is the product of supply voltage and the supply current. The supply current is taken as the average of the high level supply current and the low level supply current. Speed power product. The speed of a logic circuit can be increased, that is, the propagation delay can be reduced at the expense of power dissipation. We will recall that when a bipolar transistor switches between cutoff and saturation, it dissipates the least power, but has a large associated switching time delay. On the other hand, when the transistor is operated in the active region, power dissipation goes up while the switching speed decreases drastically. It is always desirable to have in logic family two values for both propagation delay and power dissipation parameters. A useful figure of merit used to evaluate different logic families is the speed power product expressed in picojoules, which is the product of the propagation delay measured in nanoseconds and the power dissipation per gate measured in milliwatts. Noise margin. This is a qualitative measure of noise immunity offered by the logic family. When the output of a logic device feeds the input of another device of the same family, a legal high logic state at the output of the feeding device should be treated as a legal high logic state by the input of the device being fed. Similarly, a legal low logic state of the feeding device should be treated as a legal low logic state by the device being fed. We have seen in earlier discussions while defining important characteristic parameters that legal high and low voltage levels for a given logic family are different for output and inputs. Figure here shows the generalized case of legal high and low voltage levels for output and input. As we can see from the two diagrams, there is a disallowed range of output voltage levels from VOL maximum to VOH minimum, and an indeterminate range of input voltage levels from VIL maximum to VIH minimum. Since VIL maximum is greater than VOL maximum, the low output state can therefore tolerate a positive voltage spike equal to VIL maximum minus VOL maximum and still be a legal low input. Similarly, VOH minimum is greater than VIH minimum and the high output state can tolerate a negative voltage spike equal to VOH minimum minus VIH minimum and still be a legal high input. Here VIL maximum minus VOL maximum and VOH minimum minus VIH minimum are respectively known as the low level and high level noise margins. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt that the two most popular transistors used in ICs are bipolar and MOSFET transistors. In general, ICs made from MOSFET transistors use less space due to their simpler construction, have very high noise immunity and consume less power than equivalent bipolar transistor ICs. However, the high input impedance and input capacitance of the MOSFET transistors result in longer time constants for transistor switching speeds when compared with bipolar gates, and therefore typically result in a slower device. We also discussed the characteristic parameters of TTL and CMOS family of ICs, where we learnt that the noise margins, power dissipation, fan out, propagation delay, etc. So that is it for today. See you in the next lecture with more on combinational logic. Thank you very much.